Hi everyone, welcome to another video with I Learn Engineering. My name is Leslie. Today we're going to be looking at logic gates. There's something that's very important for computer science and something that we all need to know. So let's dive in. Just before we start with logic gates, I think it's important that we all understand how computers think and what they understand. So they don't think like us. They're not people. They don't think in English or French or Chinese or anything like that. They think in ones and they think in zeros. And that's all they understand. And the ones and zeros basically denote the presence or absence of an electrical signal or a pulse, if you like. And that controls all the different units inside the computer. So because a computer just thinks in ones and zeros, that only gets us so far. Whenever we're creating computer programs and computers are operating, the ones and the zeros will say, yes, there's an electrical pulse, no, there's not. But we like to put things together and create more complex tasks for computers to follow. And then we can do all of the things that we do every day. So there are different logic gates that we need to be aware of. We have and, or, and not as the three basics. So we'll look at them first. So if we have an and gate, I'll just put and up here so we know. So you'll hear people talking about and gates a lot. For an and gate, they will have two inputs and one output. So normally we have the inputs, we will have A, we will have B. There are two inputs. And then we'll have our output, which we'll denote as C. So for our AND logic gates, we need to input our ones and our zeros so that there's every combination of 1 and 0 across A and B. So if A is 1 and B is 1, that's one variation. If A is 1 and B is 0, that's another variation. If A is 0 and B is 1, that's our third variation. And then lastly, we'll have A is 0 and B is 0. So they're all of the combinations that we can have of ones and zeros coming in with A's and B's. And then in terms of our output, we've got one output. And how the AND gate works is that we need both of the inputs to be true for the output to be true. So if we think that we have a 1, so that's going to equal true. So 1 is true, something is there is the presence of a pulse. And then 0 is denoted as false. So we need two trues to have an output of true because it's something and something. So A and B. If only one of those is true, our output then is false. So how that would work in our logic gate is then we look at A and B. So for our first line, we've got 1 and a 1. So A is true and B is true. So that means that C is true. If we look at our second line, A is true and B is false. They're not both true anymore. So here we're going to have a false. If we look at our third line, A is false and B is true. Again, they're not both true. So that's going to be a 0. And then lastly, our last line, neither of them were true. So that's also going to be a false here at the bottom. Alrighty. So it would just look like that. So that's our AND gate. That's the most common gate that we have for logic gates. If we want to look at an OR gate then, so let me just rub all of this out and we'll look at our OR gate. So with an OR gate, again, we have the same thing. We've got our two inputs and we have one output. So they start off the same, which is handy, gives me less to draw. And again, 1 is true and 0 is false. So this will be our OR gate. And what we have for our OR gate is that the inputs are going to look the same. So again, we have our combination. So if A and B are 1, if A is 1 and B is 0, if A is 0 and B is 1, or if A and B are both 0. So we start off exactly the same as with our AND gate, but this time instead of both inputs being true, only one input needs to be true. So if A is true but B is not true, we're still going to get the result of true because it's A or B this time. But that also works if both are true. So what can confuse people sometimes is they think, well, A is true, B is false. That's fine, I understand that. If A is false and B is true, I understand that. But if both are true or both are false, then what happens? And what we can see here is that if A and B are both true, C will be true. So even if both are true, that's totally fine. If A is true and B is false, we're going to get it true. So you can see already it differs from our AND gate. If A is false and B is true, we're going to get a true. And then if both of them are false, we get a false. So in the first case of our AND gate, everything had to be true. And we found in this case that we only had one true result in C, which was line 1. And the rest of them were false. With the OR gate, as long as at least one is true, then we have our true result in C. So that's our OR gate. You can see it's slightly different. So if we lastly look at a NOT gate, and these are the 3 basic gates. There are some that are like a combination, if you like. So I'll just start these again. The difference with the NOT gate is that we have one input and we have one output. So with the NOT and with the AND and the OR, we have 2 inputs and 1 output. With the NOT, we have 1 input and 1 output. So a combination of our input and output, actually just rub that out again, so it doesn't confuse us. So in this case, A is going to be our input and B is our output. So in terms of combinations of inputs, that's all we have. It's either a 1 or a 0 now, because we just have that one input. So with the NOT gate, if you think of a NOT gate as almost like an opposite, it's going to reverse whatever we have. So for the top one, for A being 1 or true, if we reverse that, that means B is going to be a false. And with our second line, where A is a false, we reverse that, it means B is going to be a true. So the NOT gate is the anomaly out of those 3 basic gates. It's the only one that has that 1 input, 1 output, where the other 2 have the 2 inputs and the 1 output. So they're the 3 basic logic gates, and we can put those together. We could say, oh, we're going to have A and B as our inputs, and then we'll have, an AND gate, and whatever the output is, then we're going to feed that into a NOT gate and end up with something different. So we can put the gates together in those ways. We can have what we call NAND gates, so not AND gates. We can have NOR gates, so not OR gates, and things like that. So we'll have a look at those now. I'll just rub this out. Here we go. So the 3 gates that we've looked at, the AND, OR, NOT, are the common ones. With the NOT AND and the NOT OR and all those kind of things, they are still using the 1 and the 0 that we've got. So 1 is still true, 0 is still false. That doesn't change. So our gate is, if we look at the NAND first of all, and that is an abbreviation for not and. basically. So it's a NOT and an AND gate together. So we have our input A, we have our input B, and we're going to have one output. So it's the same as we have with our previous AND gate. So, but this time I'm going to have our output as X. So A is our input, B is our output. And again, we'll have the same combination that we had before. So all our different combinations of our ones and zeros. That line a little bit longer. So in our previous AND gate, our top row, so 1 and 1, we would have got a true before. But this time we're putting it through a NAND gate. So we take what we would have got with A and B before, so they would have been true, and then we're going to put our NOT logic on that. So in this case, instead of us getting a 1 that we would have had before, we're going to get a 0. So we take the 1 and 1 is true, and we reverse that because we put that through the NOT gate. So you can see already that we take the two gates and we're putting them together. Then for the second one, normally we would have A or B here. You know, they're not both true, so we would normally get a 0. Because we reverse it, we're going to get a 1. Same on our third line, where we normally would get a 0, we're going to get a 1. And on the last line previously we had a 0 because neither of them were true. We're going to reverse it this time and we get a 1. So previously with our AND gate on our top line here, we would have got a 1, a 0, a 0 and a 0. You can see that this is the other way around. So it's exactly the opposite. And if I rub this out and then we look at the NOR gate, let's see if we can guess what the NOR gate is. It's pretty simple, pretty self-explanatory, I'm sure. So this time the NOR gate is the NOT OR. So again, we still have our 1 and our 0, our true and our false. We're still going to have our combination that we would have normally. Let's put those in. Alright, so we still start off in the same way. And again, what we have for this gate is that we have our OR gate and then we have a NOT gate combined. And we have them, you know, kind of in combination with each other now. So previously we would have had for a 1 and a 1. As I mentioned, this can confuse people where they think it's A or B, but they're both true. So what would that be? So normally for the OR gate, that would give us a true because it's at least A or B. But because we've added the NOT on, then here we're going to get the 0 instead. For the second line, A is true, B is false. So that would have previously been a true because it's A or B. But because we have our NOT, instead of it being true, it's going to be false. Our next line down, it's the same. So we would have had A is false, B is true. That would have been a true. But we're going to reverse it this time. And we're going to have a false. And then for our last line, previously we would have had a false there. Because neither of them were true. We're now, because we've reversed it, we're going to have a true. So you can see before with the OR gate, we would have had true, 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 and false. And now we have false, 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 and true. So the NAND and the NOR gate are not as commonly used as the AND or NOT, but they are still pretty common. What sometimes people would do, I'll just rub all of this out here. You'll see this sometimes potentially where people would have two. So these tables that I'm using here, they're called the truth table, and they allow us to see the truth of what our gates are doing. So what we might have had before is up here had our table. We would have had A and B and C, and then we would have had our our ones and zeros, whatever way we had put these in. And then over here we would have had our NOT gates. We would have taken what was coming out of this previous gate with our AND or, written those in, and then over here would have reversed it. So you'll sometimes see them created like that as two completely separate truth tables, where if we put the NAND and the NOR gate, it's the two truth tables added into one, instead of having them as two separate tables. So that is a quick whistle-stop tour of logic gates. Hopefully you've enjoyed this video. I've really enjoyed telling you guys all about logic gates. Keep an eye out for future videos where we're going to be covering more